So let's continue a little bit. Random packing of particles with continuous size distribution. We talk about mono-sized, everything the same size. We talked about bimodal distribution, two sides, one large, one small, but each of them is the same size. Now, in reality, quite often we have continuous size distribution. Okay, many practical powder have continuous size distribution, and because they are continuous quite often, they could in principle, read to yourself, in principle leads to very high packing density, but in reality, not really. Okay, normally the wider the size distribution, the higher the density. And the drawbacks of using particles with very wide size distribution is that quite often you have non-uniformity in grain body, gross non-uniformity in sintering, which is not what you want. Here I'm showing, you see kind of some region, I have particles this size, some region I have particles that are strongly bonded together, but quite often when they pack, they don't want to pack very dense. You have huge microstructure defect within them. And by sintering or heat treatment, you cannot make up for these type of defects. And it will remain as a big pore, which if you want density, high density, this is so-called detrimental. If this is why sometimes people want so-called more uniform size distribution or narrower size distribution, because they can quite often avoid large defect as compared with this one. Here we have large gross defect. Here, more or less uniform. You see what I mean? More or less uniform. Even for pores, they are more or less the same size, which means the mechanical property would be more or less uniform throughout. For here, this region, the mechanical property will be very different from here if you do so-called nano indentation or something like that. Make sense?